Hey everybody, welcome back to chemistry. And so we're continuing on through chapter 11, and now we're going into a new description of how atoms can bond. It's called molecular orbital theory. So one thing to sort of get us oriented first, let me kind of point out some basic details of how molecular orbital theory differs from the theory we just learned about how atoms bond, which is called valence bond theory. So what we learned is that it is possible that when atoms get close enough that their atomic orbitals between the different atoms can overlap. And that region of that overlap between the nuclei of the atoms where the bonding electrons reside is called a valence bond. That works out pretty well for describing the properties of many molecules. But the problem is that for a lot of molecules, the valence bond model does not well describe the properties or the observations made with a particular molecule. So we're limited to how far we can use valence bond theory. And because of that, when people realized this, a new theory was developed, which is called molecular orbital theory. So this is a completely different theory to describe how atoms can bond together to form a molecule. And so the basic idea is this. When we're looking at valence bond theory, we see that you have individual atomic orbitals associated with the nuclei of atoms. And these orbitals will get close to one another. And in that space where they're close, that's where you form the valence bond. Molecular orbital theory says something completely different. It says that when you have two atoms and they get close to one another in space, what will happen is their atomic orbitals will mix together. And then what will happen is after they mix, new orbitals are created. These orbitals are different in the sense that a particular molecular orbital has the ability of being around two nuclei at once. And so what that predicts is that if electrons occupy that molecular orbital, those electrons can wander around completely through the entire molecule. They can be between the nuclei, they can be on the outside of the nuclei, they can just wander about through the entire molecule. And when electrons are said to do this, they are said to be delocalized. And we'll talk a little bit more about that in a second. But one reasonable question to ask is, why do we need molecular orbital theory? Where does valence bond theory fail us? Where are the examples where with some molecules, valence bond theory doesn't really describe the properties of the molecule very well? So let me just give you a couple of examples of this. So for example, valence bond theory does a great job of describing how two hydrogen atoms can bind together to form the H2 molecule. And so the H2 molecule we can represent with this Lewis structure. And then also, if we wanted to, we can talk about the overlap of the two 1s orbitals from the two different hydrogen atoms and see that the valence bond forms in that area of overlap. Now, what valence bond doesn't do very well is it doesn't really explain how is it that you cannot form a diatomic helium molecule. So you can form H2 like this, but you cannot form a diatomic helium molecule, say with a double bond for the 4 electrons in these two helium atoms. Valence bond theory does not explain very well why this cannot form. So that is a problem with valence bond theory. And then what we can do instead is we can use molecular orbital theory to explain very clearly how it can be that H2 molecule forms, but the He2 molecule does not. Okay, another thing that valence bond theory can do is it can provide another explanation as to why it takes a lot more energy to break up some molecules into atoms compared to other molecules being broken up into atoms. So for example, you know perhaps from studying bond dissociation energies is that when you increase the number of bonds between the atoms, say from 1 bond to 2 bond to 3 bonds, it's going to take a lot more energy to break the bond. So for example, with diatomic oxygen, it has 2 bonds between the oxygen atom, and it requires some energy to break those bonds to release the oxygen atoms. With diatomic nitrogen, it has 3 bonds that connect the nitrogen atoms, and it requires even more energy to break those 3 bonds to release the nitrogen atoms. So the nice thing about molecular orbital theory is it can provide sort of another way of explaining how is it that when you have certain molecules, it's going to require more energy to break up those molecules into individual atoms than other molecules. And so we'll see an example of that in a bit. And so another thing that valence bond theory fails to do is that with valence bond theory, you often predict that certain molecules will be diamagnetic, meaning that they will have no attraction to magnets. But what we find experimentally is when we're dealing with that molecule, in fact, the molecule is not diamagnetic, it is paramagnetic, meaning it's going to be attracted to magnets. And so one good thing that molecular orbital theory does is it explains why certain molecules, although you would think they would be diamagnetic, are paramagnetic. So I want to sort of describe this here in detail with this example here, which is actually, I think, pretty easy to understand. So let's go ahead here and look at the Lewis structure of diatomic oxygen. And so what you can see is that we have 2 oxygen atoms in the structure that are held together with a double bond. Each of those lines in the bond represents a pair of electrons. Now also each oxygen atom has 2 lone pairs, but the thing I want you to notice is in this structure all electrons are found in pairs, whether they be lone pairs or there would be pairs in bonds. And so what we would expect is because in this molecule we do not have a time where we have a single electron in an orbital by itself, but we have electrons in pairs, and they would be in orbitals. Because of that, we would expect the molecule to be diamagnetic. But experimentally, we do not find that to be the case with diatomic oxygen or molecular oxygen. So here's actually some experimental evidence that suggests that molecular or diatomic oxygen is not diamagnetic, but it really is paramagnetic. So look at that kind of neat picture there. And so what is going on is someone has chilled oxygen. It was purified from the air and it was chilled down into a liquid form. And someone has poured this liquid oxygen between the poles of a very powerful magnet. And so what you can sort of see is that oxygen is not traveling cleanly through between the poles of the magnet. It's being stuck between the poles of the magnet because the reason is the molecule is paramagnetic, meaning it is attracted to a strong magnetic field and it'll be attracted to the north and south poles of the magnet. So what we can see here is that in fact, yes, that oxygen is paramagnetic. So we need a new theory that can explain how it could be that despite the fact that the Lewis structure of O2 shows all pair electrons, how could it be that it's paramagnetic? And so what we might expect to see is as we're doing this new model, molecular orbital theory, that maybe we'll see orbitals in some fashion maybe just have single electrons. That would allow the oxygen molecule to be paramagnetic. And so we'll go on from there. Okay, so now I want to talk a little bit more about how molecular orbital theory differs from valence bond theory. So let's just take a look at a simple example again. We'll take a look at here the formation of H2. It's also called diatomic hydrogen. And so you already kind of know what valence bond theory says, how this molecule forms. And so we'll have, say, one hydrogen atom here. The dot is the nucleus, and this circle I've drawn is the 1s orbital for this left hydrogen. And then here we have a second hydrogen atom nucleus, and then you can see that this 1s orbital from the second hydrogen atom nucleus, it overlaps with the first 1s orbital. And so this area of overlap here between these 1s orbitals of these 2 atoms is where the valence bond forms. And so here is where you find the pair of electrons here between the two hydrogen atoms. And so basically valence bond theory does a great job of describing the properties of H2. Now, another thing that it does a pretty good job of describing the properties of is a molecule called methane. So the formula for methane is CH4. And so I'm going to draw a three-dimensional picture of that. And so we have carbon here. I'm going to stick a hydrogen up here, a hydrogen off to the side like this, and then a hydrogen heading out toward me like this, and then a hydrogen going into the board. So we kind of know a little bit at this point that here, to form valence bonds between the carbon and hydrogens, that something new has to happen to the atomic orbitals of the carbon atom. You may recall that when carbon is not bound to any atoms at all, when it's all by its lonesome self in space, it will have s orbitals and p orbitals. But as soon as it binds these four hydrogen atoms, what happens is that a s orbital and three p orbitals of carbon's second energy level mix together. And when they do, they create four new orbitals called sp3 orbitals. And so I'll draw that out here. So we have carbon here. So I'm going to draw a hydrogen here like this. And so the hydrogen here is in the 1s, has the 1s orbital here. And so what you can see is that carbon will create this new orbital called an sp3 orbital here, and there's a large lobe attaching to that hydrogen, and then a small lobe on the other side. And then the same things will happen to these other three hydrogen atoms, in that you have the sp3 orbital going out to the hydrogen, same thing here, and then going into the board here, is going out to that hydrogen. And so here, this region here of overlap between the sp3 orbital and the 1s orbital of hydrogen, this is where you form the valence bond. And so if we wanted to, we can say that this valence bond that forms between the sp3 orbital of carbon and the 1s orbital of hydrogen, you can call it, if you want, an sp3s valence bond. Okay. So let's talk about now how molecular orbitals are different. How are they different than valence bond orbitals? Okay, so with molecular orbitals, something completely different happens. And so if you have two hydrogen atoms that get close together, I'm drawing the two nuclei for these two hydrogen atoms. Through a process, which I'm just going to show you in just a second, is that you have these two 1s orbitals that were associated with the individual nuclei. They mix together and they form two new orbitals. Let's draw one of these orbitals first. And so I'm drawing one of these orbitals, and the fascinating thing you can see is that this one orbital is different than what we've seen before. What you can see is that this one orbital actually holds the two nuclei. And so this orbital that is formed in this process, and we'll talk more about this in the future, is called a bonding orbital. Now, another orbital is formed, and so it has a different appearance. And so here are the two nuclei again. And so here, this time, we have some electron density kind of surrounding this nucleus. And then we have some electron density from the same orbital surrounding that nucleus. And so this is called an anti-bonding orbital. But the key thing here is to notice this difference. What you can see in the valence bond is that this is the area of overlap from two different atomic orbitals. Now, with molecular orbitals, what happens is that you create, in this case, two new molecular orbitals, but this time a molecular orbital is not associated with one particular nucleus. You can see that one molecular orbital holds basically two nuclei, and then here, this is actually considered to be one orbital, and it holds two nuclei as well. So this has some interesting ramifications as to where the electrons are found in molecular orbital theory. So in valence bond theory, you find the electrons in between the nuclei because that is where the orbitals overlap. But look, if you have electrons in the bonding orbital, you can find them in between the nuclei, but you can find them outside the nuclei. You might find an electron here, you might find another electron there, for example, and if the electrons are in the antibody orbitals, same deal. They will not be necessarily found between the nuclei. In fact, with the antibonding orbitals, for a reason I'll show you in a minute, you cannot find electrons between the nuclei. There is a region here that electrons cannot be found, and it's exactly between the nuclei and the antibonding orbital, and this is called a nodal plane. So a nodal plane is just a plane in space where you cannot find electrons, and so we'll talk about why that is the case in a minute. Okay, so moving on. So what I'm going to do is, at this point, I want to just pull off the slide and show you some diagrams that I have here on the right. So here they are. Whew. Okay. So what I want to do is I want to talk a little bit about some of the details about how is it possible that you can form these molecular orbitals. So we're going to talk about the process by which you take two atomic orbitals, two 1s orbitals for hydrogen, and form the bonding molecular orbitals for the hydrogen atoms, which is described on the left. Then we're going to talk about taking those same two atomic orbitals for hydrogen and then sort of dealing with them in a different manner and forming the anti-bonding orbitals that you see on the right. So let's focus in how the bonding orbitals are created first. Okay, so what I have here on the right at the top is a picture of the bonding orbital, which is a kind of molecular orbital. So the thing I want you to notice with the bonding orbital is that we have the two nuclei of the hydrogen atoms, and then we have the single orbital which encompasses these two nuclei. So the question is, how do we take two hydrogen 1s orbitals and combine them to form this molecular orbital? So what I've done at the very bottom here on this diagram is I've tried to draw on individual graphs about how this process occurs. So let me try to explain it starting with this lower graph. So on the lower axis here, I have the x-axis. And so basically the x-axis follows the distance through these nuclei. And then here I have some kind of y-axis which plots the magnitude of the function I'm kind of following. So what I want to do is first focus in on this lower graph. And so what I've tried to do is I try to give you an idea of what the graph for a 1s orbital looks like. And so the 1s orbital from, say, the left hydrogen is in blue, and the 1s orbital from the right hydrogen is in red. And so what I'm indicating is that as you go across the distance here, you can see that the value of this function that describes the 1s orbital goes up, and then it goes down again. And same thing with the value of the function that describes the right 1s orbital. It goes up and it goes down again. So we have these two nice simple graphs of these 1s orbitals. Now, what is this weird thing here, this Greek letter? This is the Greek letter psi. And what psi is, it means is this is sort of a particular kind of graph that can be made of curves, and it can be made of waves. And so these are called wave functions. And so here, this particular wave function that describes the 1s orbital is not so much a wave this time, it is a curve. But in spite of that, it is still called a wave function. Now, what we're going to do is we're going to take these functions, and then what we're going to do is we're going to simply add these functions together. And so what I've done that here in this next graph up. And what I've done, say for any point here, say here this point on the x-axis, I'm adding the y value of the blue line to the y value of the pink line, and that gives me the total value here. And so what you can see is when I add these two functions of the 1s orbitals, I get this yellow line here. And so that's beginning to maybe look a little bit more like the final bonding orbital. Now, the final step to understand where the electrons are found in this orbital is it's not really enough to just add these two orbitals up to give me this graph here, this function. You have to square the function. And so I've done that. Here I've gone from psi to psi squared. I have squared the function. And when you square this function, then this graph tells you where the electron density of the electrons are around the nuclei of the atom. And you can see there's a peak of electron density here on the left nucleus and a peak of electron density here on the right nucleus. And so the y-squared graph, again, gives you sort of the final picture of where the electron density is in the bonding orbital. So what we have done is kind of a process of constructive interference. Let me explain. So what you can see is all I've done here in this graph to produce the bonding orbital is I added these functions, 1s plus 1s. It's sort of like adding waves, and when the peaks of the waves overlap each other, then you get a larger peak, and so it's constructive interference. And you can sort of see that it has happened here. And when you square that, it just increases the effect. Now, this is sort of seen in a slide we're going to show you in just a little bit. But now let me go over and talk about how the antibonding orbital is formed. So what you can imagine here is that maybe it might be something that's opposite of how we form the bonding orbital, and that is true. So with the bonding orbital, while we added these 1s orbital wave functions, here to form the antibonding orbital, we are going to subtract the 1s orbital wave functions. And so here, go into the lower right picture here, we have a graph of the function of the left 1s orbital in blue and of the right 1s orbital in pink. Now, instead of adding them together like we did here to form the bonding orbital, we're going to subtract them. So let's see how we might, as an example of a point, let's see how we might do that. Let's notice where the pink line and the blue line meet, which is exactly between where the nuclei are. So it's this point here. If we subtract the blue line from the pink line, we should, because they have exactly the same y coordinate, we should get 0, and we see that. So when you subtract the pink from the blue, this is the line you get. And so notice I've sort of plotted in a slightly different graph here. Here the x-axis is at 0, and I have positive y values here and negative y values there. And so what you can see is that when we subtract these 1s orbitals, you get 0. And then when you can continue to subtract, you actually get negative values. And so that's what it looks like. But in the end, the electron density does not so much reflect this wave function here. It reflects this wave function squared. And so when you square this, what happens? So the positive peak gets squared. It stays positive. It just gets a larger value. Here, when the negative peak is squared, remember, when you square negatives, negatives become positives, and they also increase in magnitude. And so this is the peak you'll get here. But note that the 0 is still 0. So that's why here in the antibonding orbital, we have a place where you cannot find any electrons. And this is the nodal plane that is between the two nuclei. We cannot find any electrons there. Okay, so I'm going to go back to the slide now. And so here I have sort of a description of how you get the bonding orbital formed. And so let me just kind of focus on that.